There are two types of Hess's Law problems. Now, I call the first type a puzzle piece Hess's Law problem, and you'll see why in a couple seconds. And the other type of Hess's Law problem is what I would call a heat of formation law problem. The difference is that in the puzzle pieces problems, the problem itself will give you a set of reactions, where in the heat of formation problems, you are going to be given a table of information, and that table of information will include heats of formation, which we'll talk about in a next video. So when you are trying to solve puzzle piece problems, there's some rules that you must know. So if you take a puzzle piece reaction and you flip it, so you change the products into the reactants or the reactants into the products, then you must change the sign of that reaction's enthalpy. So for example, let's say that you are told that a reaction pumps heat out, it's exothermic. And you're told that, they write it on the paper for you. And you decide that you actually want this reaction to run in reverse. Then when you play it backwards, instead of pumping heat out, it's going to absorb heat. And so it will go from being exothermic to endothermic. So if you switch the way a reaction runs, which you are allowed to do, you must also switch whether it is exo or endothermic. The second rule is that if you need to run a reaction more than one time, say you have to do it twice or 3 times, then you have to multiply the reaction enthalpy by the number of times you do the reaction. So if you were to do a reaction 1 time and you get 100 kilojoules, running it 3 times will get you 300 kilojoules. And I'm sure that sounds like total craziness, but let's take a look at a set of examples. So here we have a reaction up here, and they want to know, what is my enthalpy for this reaction up here? N2H4, which is hydrazine, plus CH4O, goes, I think this is formaldehyde, nitrogen, and hydrogen gas. So then they give you a set of reactions underneath here and some enthalpies. And what you're supposed to do is to combine these reactions to give you the top one. So remember how I said that chemical reactions are state functions. They may occur in multiple steps, but all we need to know is, what did you start with and what did you end with? Okay, and as long as you start in the right place and end in the right place, it does not matter what happens in between. Okay, so I need to get a reaction that starts with N2H4. Now, my first hint for you is to search through all the reactions you have down here and to identify orphans, things that only occur once. Like here, the ammonia occurs in 2 separate reactions. Hydrogen occurs in all three reactions, actually. So you don't care about those things because there's lots of different ways that you could make hydrogen occur in a reaction. But there's only one hydrazine, and you need it to be in the right spot. Okay, we actually need it to be a reactant, and in this one, it's a product. So I'm going to flip this whole first reaction and write it backwards. I'm going to write N2H4. Now it's a liquid, but it's a liquid in my original equation, and nowhere else does it occur with any other state. So I'm not really that worried about it. It may become important that you remember that, oh, wait, this is a liquid in some problems, but in this one, it does not matter. So here we have H2, and this is now going to produce 2 NH3s. So I've just taken this reaction and written it backwards. I'm also going to write myself a note that I have flipped this thing, and I'm going to put a negative sign here. If I could squeeze it in over here, I would. But I just need some way to remind myself when I get to the end that this is not a positive 22.5 anymore. It's a negative 22.5. Okay. I also have another orphan, which is this CH2O, which I think is formaldehyde, and that needs to be a product. So I have to flip this reaction as well. Okay, so I'm going to take my CH4O and I'm going to make some CH2O and some H2. And since I flipped that reaction, I'm also going to make myself that note saying I need to make this negative this time. So now I've introduced some weird stuff. You'll notice that my original equation does not have an NH3. So I need to get rid of it. And the way that I can do that is if it's a product here, if I could cancel that out with a reactant, then like it would be as if it never occurred. So I'm going to take this middle puzzle piece and I'm going to leave it as it is. Goes to N2 plus 3H2. And you notice how I made the three arrows line up? That's so that I can easily see what's going to cross out and what's not. So I have two NH3s that become two NH3s as products. So actually, if I change colors here, the NH3s that I started out with, I end up with. So it's as if they never did anything. They're not part of a chemical reaction. Okay, this H2 here, I started out with an H2 and I ended up with an H2. So that H2 also did nothing during the reaction. And if I add up everything that's left, I have an N2H4 and a CH4O that becomes a CH2O and N2 and 3 H2s, which is exactly what I need up here. Okay, so I've basically said that I can make this reaction happen in 3 steps. If I take some hydrazine and some hydrogen, I can make ammonia. And then I can take the ammonia and make N2 and H2s. And I can take some CH4O and turn that into some formaldehyde. So I can combine these 3 crazy things into one. So when I do that, I'm going to take my original enthalpies, my original heats here, and I'm going to write them down as negative 22.5, negative 81.2, and positive 57.5. And if I put those all in my calculator, I believe that I will get 46.2 kilojoules. Now, these things were written as kilojoule, which is good, but you will also see in AP that they are written as kilojoules per, oops, I said that wrong, sorry. Let's erase that. Kilojoules per mole reaction. Now, if you see this, kilojoule per mole reaction, what it means is that this thing is really not a kilojoule. It is a kilojoule per mole. But the question is, mole of what? Is it the 3 moles of hydrogen? Is it the 1 mole of nitrogen? Well, these are all products. So no, like you'd never base something off of the product, but you'd base it off of what you put in there. And in this case, it's pretty simple. This is both 1 mole or 1 mole. So it seems obvious that 1 mole of hydrazine here would produce 46.2 kilojoules. But that's not the whole point. Hydrazine on its own can't make this. It's hydrazine and CH4O. So what AP decided was, if we ran this reaction one time, so we're going to take this whole reaction, run it once. Every time you run it, you get 46.2 kilojoules per mole reaction. That's what they mean by that. Okay, let's do one more problem here. So here is my reaction. 1 half H2 plus 1 half Cl2 gives me HCl. And your first thought should be, what is going on here, Sturman? A half of an H2? That's illegal. My chemistry teacher last year told me I'm not allowed to use fractions. They were right, but they also did not teach you thermodynamics or Hess's law. When you're doing thermodynamics, you can use anything you want as a coefficient. If you use a fraction, that's fine. If you wanted to use like complex numbers, that would be fine too. You just need to make sure that whatever you do with the puzzle pieces down here gets you what they are after. So the reason they did this is because they really only want to find out how much energy is made producing one hydrochloric acid. If we did this normally, like you would have done it in honors chem, you would have produced 2 hydrochloric acids, and the author of this problem doesn't want to know that. They just want to know how much energy would I get out for 1 hydrochloric acid. Okay, so let's look for some orphans here. I've got a COCl2. That does not appear. Oh, it appears here. Okay, so I don't care about that thing. HCl only appears 1 time in all of these puzzle pieces, and it's on the wrong side. So I'm going to flip this. I'm going to take the middle equation and say H2O plus Cl2 goes to 2 HCl's plus a half of an O2. And at this point, I don't want you to worry about the fact that this is 2 HCl's. I just want you to concentrate on the fact that HCl is in the right place. It's a product. I'm also going to note to myself that I just flipped that thing, and so I'm going to make it negative. Okay. I have also an added bonus that I have some chlorine in the right space too, right? I've got Cl2 as a reactant, so double bonus there. Now, I don't want any water. So I have to start figuring out, how do I get rid of this water and this half of an oxygen? Because it doesn't appear in my final equation. So I could say, well, let's take this one right here, this bottom one, and leave it as is. That will help me to get rid of my oxygen. So if I go CH2Cl2 plus H2 plus 3 halves O2 goes to COCl2 plus 2 waters. That'll help me get rid of, like, ooh, this water kind of cancels with that water, and this oxygen kind of cancels with that oxygen. But I don't see an easy way to make that happen yet, so I'm going to let it go. And besides, I have bigger fish to fry. I've got the COCl2 and this crazy CH2Cl2 thing that I don't want. Oh, but I do notice that the first equation helps me kill those off. So if I keep that the same, now I can start canceling some things out. The COCl2 and the COCl2 as a product cancel. This dichloromethane cancels over here with the dichloromethane. I have an H2 as a reactant, which is good. I have a Cl2 as a reactant. I've got 1 water and 1 water. So that's 2 waters. Ooh, and I have 2 waters over here, which cancel. So my 2 waters and my 2 waters will cancel. And over here, this thing is 1.5 oxygens. And this thing is 1.5 oxygens, so they cancel. And if I rewrite this, I get H2 plus Cl2 goes to 2HCl. I only made one change. I have this negative 105. I have the negative 402. Oops, sorry, negative 402.5. And I have the positive 47.5. And if I total those all up, I get negative 460 kilojoules. Now, is that the answer? No, because I didn't make what they asked me to make. I made double. So you notice that I have H2Cl2 both as ones. I need to get them to be halves. So I need to divide this whole reaction by 2. That will give me a half H2 plus a half Cl2 and 1 HCl. But if I divide a reaction in half, remember, one of my rules is that if I divide something in half, I must also divide the enthalpy in half. And half of 460 is negative 230 kilojoules per mole or kilojoules per mole reaction. It's important in this case what you say, because we only have a half a mole of H2. So it would get confusing if you said that it was negative 230 kilojoule per mole, because then the reader might say, was that per half a mole? But when you put the mole reaction here, you're saying, I told you to do this. If you do this exactly as I wrote it, you will get negative 230 kilojoules out. Okay, next video we're going to be looking at heats of formation.